So hello everyone, I'm Christoph and I'll be explaining the Anoma SDK today. So we'll go over three things. First of all, the architecture of an Anoma application. That's important because an SDK is used to build applications. Then I'll explain what the Anoma SDK really is, and by what it is I mean how does it help you building applications, and then finally I'll show a very code-riddled example of an actual Anoma application. So the example I want to use throughout this presentation is an over-engineered counter. So the counter we want to create allows you to create counters, increment counters, encrypt the counters, and some additional rules. They're not really that important right now, but the idea here is that we want to write some application code that will build our over-engineered counter, and this URL actually explains it in painstaking detail what the actual counter is. But let's go over the architecture of a counter application. So you want to build this counter application, you will need three things. First of all, you will need general purpose logic. This general purpose logic will define things like how do I increment a counter? What happens when I click a button to increment this counter? You will also need to interface with Ethereum because, as Artem explained, the protocol adapter lives on Ethereum. So if you modify a counter, if you want to create one, somehow this information will need to end up on Ethereum. And you will also need the Anoma resource machine to deal with these resources that will represent your counter. If we go one layer deeper, we know that the Anoma resource machine consists of Anoma resource machine data structures, resource logics, and that the logic you need to actually communicate with Ethereum means you need bindings that convert EVM bytes into resource machine bytes and vice versa. And you will also need logic to communicate from within your application to Ethereum, basically submitting a transaction or reading information from Ethereum. What is the value of my counter? And again, your general purpose logic. So if you want to build all this, that's going to be a lot of work. So the SDK is designed to help you in taking away all the stuff that we think is irrelevant to building an application. So if we look at the previous diagram, the stuff that's now yellow is the thing that the Anoma SDK will take care of for you. So what's left? The general purpose logic. We cannot do that within an SDK because that's completely dependent on what kind of application you want to build, and the resource logic. So as a summary, the resource logic is the set of rules that governs what resources in your application can do. So we're designing the over-engineered counter. So the resource logic, in our case, defines what can happen to a counter. Some of these rules are you can only increment it by 1. You can only create a counter out of thin air with value 1, so you cannot create a counter with value 10 to start with. And you can only increment your own counters. So we cannot define these rules for you, so you will have to provide them. And your general purpose logic. But converting from EVM bytes to resource machine bytes, we do it for you. Providing you functionality to actually submit transactions to Ethereum, we also do it for you. And then the ARM data structures, of course, we can provide them for you, so you don't have to re-implement resources and operations on them. So this is basically what's left. If you want to build an application, use the SDK, define your resource logic, and define your general purpose logic. That's it. So I think that's a pretty good deal if you want to build applications. And then, point of contention actually, internally, the general purpose logic and the SDK are written in Elixir. Why? There's a very good reason. We're an Elixir shop, and we also use the SDK, so we need it in Elixir. And it's just a really good language to build general purpose applications, so why not? The only thing you need to do is write resource logics in Rust, because the resource machine itself is written in Rust, and you can only generate proofs over Rust code. But you win some, you lose some. So now I'm going to go over a simplified example of the counter. So the actual code, you can find this code online on the GitHub repository, but I have to admit I forgot to put the link on the slides. But the Anoma GitHub, you'll definitely find it under counterexample. And the code that follows is somewhat simplified, but you can find the actual code online. Okay, step 1, we need the SDK. You just add the Anoma SDK as a dependency to your Elixir application, and you're done. Step 2 is writing resource logics. So I mentioned before briefly that the resource logics define the rules that apply to the resources you manipulate within your application. And resource logics, you can think of them as basically a very fancy predicate. And the input to this predicate is called a witness. And the predicate we define wants to know, is this resource you're using, in this case a counter, is it a consumed one? What's the old value? What's the new value? And the nullifier keys, and then some Merkle things. But I don't want to go into too much detail here. So this is the input to our resource logics. Okay. The actual resource logic, so the rules, are defined here. So the first thing we want to check, the resource I created and the one I consumed, are they actually created within the same action in the same transaction? Just checking, is the root the same for the new and the old counter? If so, the resource logics continue. I'm just putting small pieces of the resource logics on every slide so I can explain them one by one. The second rule, if we're creating a new counter, that means that we actually have to consume an ephemeral counter. So an ephemeral resource is a technique in the resource machine to actually create resources out of thin air. But a transaction always has to create one resource or consume one, well, or the same amount. It has to be balanced. So if the counter we're consuming is ephemeral, it means we're creating a counter out of thin air. And then the value has to be 1, meaning you cannot create a counter out of thin air with value 5. So that's this check. Next, we have to check if you're incrementing a counter, the new value has to be 1 more than the previous value. If that's not the case, the check will fail. And then finally, we return the instance, which is basically shows that we actually proved the resource logics to be true. And once you reach this point, we know, okay, this transaction actually adheres to the rules within the resource logics we defined. And that's it. So we have our resource logics. We can actually define what a valid transaction is and what's an invalid transaction. So now all that's left is a general purpose logic. So we need to do a couple of things. First, we need to be able to create ephemeral counters if we want to create counters out of thin air. You see here, can I point with this thing? I don't know. So these resource data structures, they're all provided by the SDK. So you don't have to do any of this. The only thing you need is nullifier keys and nullifier commitments, which are just secrets you can generate. And then here, the logic reference, which is basically a reference to the resource logics we just defined. And then we create a resource, quantity 1, the value of this counter is 0, it's an ephemeral counter, a random nonce, and a commitment. That's it. If we have our ephemeral counter, we now need to create the counter we actually want with value 1. So we pass in the ephemeral counter we just created, and we switch ephemeral to false, a new random seed, and the nonce is based on the nullifier key of the ephemeral resource. This is actually kind of technical details, and we put the value to 1, because we can only create new counters with value 1. And okay, so at this point we have an ephemeral counter and a new counter we want to create. So all that's left is a transaction that actually creates and consumes them. So we call these two functions to create the counters. And then to create a transaction, you need to generate a couple of proofs. And this is where it gets kind of technical. But, well, the first thing you need to generate is the compliance proof. So this function is not provided by the SDK, but it's actually not that big of a function because the SDK provides the primitives to actually generate the proofs. So once you have the compliance proof, you need to generate the logic proofs, which are the proofs that the resource logics apply to your counter, so basically a valid transaction. And then, when you have all your proofs, you can start building the transaction object. And part of a transaction is an action, We create the actions by plugging in the compliance units and the logic proofs. Finally, we generate the delta witness, which is the final proof you have to generate for a transaction. And once we have the witness, we can generate the proof of the transaction, and we're done. Well, so this is basically it, what you need to do to create a counter transaction. So generate the 3 types of proofs, generate the resources, and that's it. So that's the basic ingredient for general purpose logics. So now you can package this in a nice web application or whatever you want to do, and you're done. If you want to submit this to to the protocol adapter, there's also the submit function, of course. So that was it. I explained to you the high-level architecture of any Anoma application using the over-engineered counter. Then I showed you what the main ingredients are you as a developer would need to implement if you want to build your own application. I showed you a minimal version of a resource logics, and I showed you the minimal version of general purpose logics. Thank you.
Thank you, Christophe, for going over the Anoma SDK and recapping what everyone was supposed to have learned at the end.
Yes.
In case they forgot. Any questions for Christophe? Yes.
Yeah, thanks, Christophe. My question is where the foreign function interface lives, if this is provided by the SDK. So when you're writing the resource logic in Rust and then the GPL, like, yeah, where does that, do the developers write that on their own, or does the SDK?
Yes, so that's actually a good question. You have to write the foreign function interface yourself. So the reason that this is so is because the SDK implements a foreign function interface to the resource machine. But let's say that you really want to, I don't know, do it in Python, you would have to do it anyway.
Right.
And the functionality that your general purpose logic relies on for your resource logic is always custom. So there's no way for us to provide a default implementation for whatever you're going to design in your resource logic. So, but the actual functions you would need to provide are just 2 of them. Proving your resource logic and verifying your resource logic. So 2 functions, that's it.
One of those was the compliance proof?
No, those are SDK functions.
Okay, those are SDK.
So
okay.
compliance proof, delta proof are provided by the SDK. Okay. The only thing you would need is this one. That's the only one you need to implement.
Cool, thanks.
Thank you for the question. Any other questions for Christophe? Going once, thrice, twice. All right,
Thank you.
let's give it up once more.